Today we have Aaquib with us, joining from the University of Colorado Boulder. Aqib's a PhD student at the Collaborative AI and Robotics Lab there, where he's advised by Professor Brad Ace. Aqib works at the intersection of explainability and HRI, aiming to leverage and enhance multimodal human-machine communication for value alignment and fostering appropriate trust within human-robot teams. Uh, he's an RSS and a HRI pioneer, and his work has earned Best Paper nomination awards from the HRI and the AAMAS communities. Thanks for joining us, Aqib. We're excited to listen to your talk, and you can share your screen now.
Thank you, Nitin, for kind introduction. So today I will be talking about my thesis work on building trust and transparency in human-robot teams through explainable multimodal communication. So whenever people think about robots, their perception is very much influenced by movies, medias, and pop culture. For examples, robots in Jetson or Small Wonder assisting people in doing day-to-day tasks, or social robots providing elderly care, or even just providing emotional support. Whereas on the other side of spectrum, we also have a lot of people asking us about us roboticists, when are robots going to take over the world? I'm pretty sure everyone here in this talk has been put in a tight spot by someone of their family member or friend about this kind of tricky questions. However, when we look into the reality of current state of robots, we find a stark contrast. In reality, the deployment of robots are still in a very early stages, especially when it comes to safety critical and mission critical applications. Robots are often confined, caged, and kept at a safe distance from human. There are valid reasons for this. So first of all, robots must provide safety assurances. We need to be absolutely certain that these machines will operate as intended without causing harm to the humans or the environment where they are deployed. Second, robots must plan for uncertainty and unforeseen circumstances because they should be able to adapt and improvise when something unexpected happens. Robots must be able to communicate their future behavior and decision-making rational so that people can appropriately trust and rely them. And lastly, and not the least, we want these machines to work with people, and therefore they must conform with the people's expectation and social norms. So this is where communication becomes crucial. Communication in robotics is generally seen as a one-way street, that is, people communicating with robots. So what I mean by that is like people programming robots to do things. And we've been doing this for a while. There has been a lot of research on how to effectively program robots, what interfaces we should use to be doing this. But on the other hand, we expect these machines to do what we want them to do. However, they can only act based on their programming or data they have been received, which may not always align with the expectations or intentions what we want them. So this is where the value alignment problem comes into the picture, or mix match expectation. To solve this issue of mental model mismatch, what we really want is for robots to communicate back to us. We want to understand their decision-making rationale, want to know what they have learned, have a clear understanding about their capabilities and proficiencies to appropriately deploy them. People generally classify this within the umbrella of explainability, but for me, explainability and communications is intertwined. Without communication, there can be no explainability, and without considering the people for whom these systems are designed for, explainability efforts may fall flat. So this brings to the focus of my research. I am exploring how to build good robotic teammates that can effectively communicate to align and reconcile the mental models of robots and humans to build trust and transparency. Okay, so therefore in this talk, I will provide an overview of two research themes. I work on. First, explores how to enable mental model reconciliation by leveraging communication. Second, explores the essence of these explanations to build trust and transparency. Specifically, we will look into how the psychological effects such as compliance and reliance come into picture based on the different characteristics of explanations. Okay, let's get into it. So the first work looks into the explainable robotic coaching framework. So this is a work I did with Shivendra Agarwal and my advisor, Bradley Hayes, which was nominated for Best Technical Paper in HRI. So consider this role life cycle. So we are good with this transition of turning a capable robot into, a capable robot into a competent, capable robot, but there is not much has been done to turn a capable robot into a competent instructor. And we want capable instructors that can engage in foresight because learning from experience can be expensive, especially when people are involved. So in this work, we were motivated with the questions about how do we turn robots into competent instructors, especially can it use its understanding to figure out yours, what is missing from it, and given this understanding, can it issue a corrective guidance in a way you will understand it? So example is in this comic strip, maybe yelling stop at Calvin is a not right approach to convince him. So to model this human belief, we generally assume humans to be rational and goal-directed, even if we don't necessarily understand their goals. What can we leverage from this assumption is a suboptimal behavior comes from the misunderstanding of the world. In other words, unexpected policy indicates a difference in reward function. So if we can correct the reward function, consequently, the policy would also be corrected. This is a common and distinct assumption which we regularly use in our work. So this was the core intuition behind our explainable coaching framework, which we call RARE, Reward, Augmentation, and Repair through Explanation. The intuition behind that is like, consider this a simple grid world. And the goal of an agent here is to maximize end reward as soon as possible. So we expect a knowledgeable, rational human to go up towards the right and collect the bigger reward. However, if we see someone doing something like this, like go up and take left, then we can assume that they don't know about the bigger reward on the right and their world model is incomplete. So problem we are trying to solve is how do we tell them people about the inaccuracies of their reward function? So we first estimate the reward function by observing humans taking action. So what we do is we subdivide the reward function into a reward component. So in this case, it would be R1 and R2, and track them as a Boolean state variable that indicates whether the collaborator knows about that particular reward component. So to give a quick illustration, so assume a collaborator is starting here. We don't know much about both the reward component. They move forward. We know something, but this wasn't an informative action. As soon as they take left, we know that they know about R1, but they don't know about R2. So we need to communicate this reward's existence to the collaborator before they finish it. We can do this in a couple of ways. So first is we can say that you're doing wrong, you're doing something wrong, and you won't get a best reward. So what this does is this indicates that a suboptimality of an action to a human, and it would encourage exploration. Second option is you can justify that advice by telling that there is a better reward in the top right corner. What it essentially does is it basically guides the planner to a particular state and avoiding a negative state. So we wanted to check the effectiveness of this reward coaching framework and the importance of justification. So we came up with this incredibly difficult game to make people play with robot in a collaborative setting, which we called real-time color Sudoku. In this game, person and robot have to collaboratively solve Sudoku puzzle while adhering to constraints as shown here. game becomes extremely difficult as it progresses because early choices have later repercussions. Most of the people could not solve the game without the help of the robots. To give a high-level summary of what we found from this, like subjectively, we found that the robots that provide justifications are considered to be more intelligent and more capable when it provided them justification for the advice which they provided. Furthermore, we also had an objective hypothesis going into this. We anticipated the people would complete game faster when a reward justification was provided, but we couldn't test it. We couldn't test it for an interesting reason, because most of the people did not listen to people's advice without justification. This was an interesting finding for us. And this was an initial glimpse into the psychological effect justification has on the people. That is, it can help prepare people's trust, but also has an ability to convince people. We will circle back on this finding later on and expand upon it. To go into a little bit caveats of this work, so rare corrects single action at a time, which is good in certain scenarios, but not scalable in many scenarios. Explanation generation, what we use is not scalable. It is exponential to state space and domain size. And finally, the explanations are agnostic to the user preference and understanding. What I mean by that, so consider this model reconciliation problems. So what I mean by that, there is a situation where there is a mismatch in mental model of human MH and the robot RH. So the explanations should first address the delta between the human model and the robot model. Second, the explanation should consider the human model or knowledge while generating those explanations. So to give an illustration how we can operationalize in one of the scenario is, so let's assume that there is a conference in this building and you are attending the event, which is shown in this image with the orange box. So assuming you're visiting it for the first time and there is suddenly a fire emergency in the building, and the agent is tasked to evacuating people out of the building. So one way an agent can do this is by listing off the room names where there is a fire, but this won't be essentially helpful to the person who is visiting for the first time. But what we can do is we can add a little bit of abstraction and overspecification in the language to come up with this new language descriptor. So in this case, it would be Southwest. What it essentially does is it makes the language a little bit more comprehensible to the person, and they can use it in much better way. So this way, by weighing different state descriptor according to comprehensibility, we can trade off between precision and utility without affecting the end outcome. And this is what our next work tries to achieve. That is, provide a framework to generate human-centric explanations for real-time policy coaching. So this is a work which is in submission. I did in collaboration with Ryan Leonard and my advisor. So in this work, we came up with a modified form of human policy coaching called SPEAR, Single Shot Policy Explanation for Augmenting Rewards. Here's the intuition. So assume a similar emergency evacuation scenario as shown here. An agent has to guide people out of this building, and there is a fire in the building. As the human is not aware of the fire, so they are operating with the faulty reward function, which is not aware of fire, and following a suboptimal path, which leads them towards a hallway that has a fire. So in this case, what SPEAR does is SPEAR leverages what we call language state descriptors to manipulate the human reward function using language. Predicates are a way to incorporate language without actually solving it. So for example, there can be a predicate called a central hallway, and we can check if there is a fire in the central hallway, and it gives back whether there is a fire or not. We can also combine predicates such as intersection of predicates to have more complex language descriptors. So in this example, Spear uses predicates for reward manipulation. That is, it finds the language descriptor that best updates the human reward function such that the desired policy is elicited. So in this case, the best approximation is to tell them that there is a fire in the central hallway. So what it essentially does is changes their reward function and leads to a desired policy, what we want. And one thing you can notice this is their update is a little bit overspecified, but we get the end result. So to check the utility of this framework, we did two broad evaluation. So first was a sim evaluation where we tested the algorithmic's performance. And the second, we tested for the explanation quality using an online user study within different domain. So for the first evaluation, we use an emergency evacuation domain shown in the left. So we tested our algorithm for similar maps over 100 episodes and compared the agent's reward before and after the Spear update for stochastic and deterministic domain. Here, the map results are shown for the map size of 25 cross 25. And we found that the Spear improves episodic reward after just one semantic update. Similarly, we varied the number of predicate count to check for computational time for different map size. And we found that Spear scales linearly with predicate count and provides several order of magnitude improvement over state of the art in terms of computational time. One of the interesting things which you can see on the left graph is that there is a discontinuity in the purple line. This happened because we were randomly generating predicates, as you can see on the x-axis. And in this situation, generation of new predicates led to an alternate solution, which was much faster to compute. Going over to the explanation quality evaluation. So we had three types of domain. So first was grid world navigation domain, fire rescue domain, and a robotic cleaning task domain. And these domains were inspired from previous work in explainable AI. For each of these scenarios, we showed three types of explanation. First, it was a direct enumeration. These explanations show a model divergence in the state space form by providing the numeric reward function. Second, exact explanation. So these explanations show model divergence in the form of semantic updates without adding any abstraction. And finally, we had relaxed explanations. These explanations abstract some details when providing model divergence update. And for we showed these explanations to people and asked them to rate them in the following subjective measures of usefulness to interpretability. And we also asked them to judge on which explanation would likely lead to desired behavior shown to them. And we found that people rated relaxed explanations higher than the other two types of explanations in all the subjective measures which I showed on the previous slide, proving our main hypothesis. Interestingly, we also hypothesized that people would prefer exact explanations over direct enumeration, rating natural language higher than the numerical reward function. But interestingly, we saw that in the grid world domain, the result was reverse of what we expect. That is, people preferred the whole numeric reward function over semantic explanations. But the trend was as expected in the other two domains, as we hypothesized. Our likely explanation for this dichotomy of result is attributed to the domain size. We think for the smaller domains, people might prefer the numeric reward function because the state space size is small. But as the domain gets more complicated, people prefer a natural language updates. Nonetheless, if we can employ abstractions properly, people prefer this irrespective of domain size. So this is what we got a glimpse in our open-ended subjective feedback, that people prefer clear, concise explanation, even if it comes with trade-off in accuracy. And with this, I would like to summarize this work. where we introduced a policy coaching framework that achieves several order of magnitude improvement over state of the art in terms of computational time. And that enables advances in much broader class of policy coaching problems. We also showed through user study that abstraction in explanation is quite useful and helpful, even if it comes with some cost of accuracy. And this completes the first part of my talk. And for the second part, I would specifically be presenting our work on how explanations have psychological effects on people's behavior and their characterization thereof. Okay, let's look into the visual explanation. So there has been plenty of work in decision support and trust in human agent teams. One of the common trends we notice is that people are prone to over-trusting systems and recommendations from them. We can see these common examples in navigation assistants, and more recently, large language models. One of my favorite example is the study by Robinette et al., where they studied people's behavior in a fake fire emergency scenario. So here, people were initially not informed about this. And what happened is that a fake alarm goes off, and this robot is guiding people out of the building. And they also created the urgency by having fake smoke. In the experiment, this robot guided people towards the dead end, and people followed the robot towards the dead end, even though they could see the exit just in front of them. So therefore, this overtrust and compliance can lead to failures or automation abuse that we need to avoid. Specifically, we want to minimize overtrust and encourage appropriate thinking in these type of critical scenarios. So this is where our next work comes into the picture. We explore the use of visual explanations for influencing human thought patterns and breaking the cycle of overtrust. So this is a work I did with my colleague Matthew Lubers and my advisor, and it was nominated for Best Paper at AAMAS 2022. Our motivation for this was an avalanche rescue domain. This is an interesting domain, which you can see there, because here there is, we have a heterogeneous teams with different capabilities working together to rescue survivors. So that is generally we have people and dogs with being who are trying to find survivor, and there is a ground crew which comes and digs them out. You can imagine in such scenario, introducing a fleet of drone would be extremely helpful for searching survivors, because drone can quickly survey the area and try to find the people and sensors, and people can just go and dig them out. This is where we came up with MARS, or min entropy algorithm for robots applied suggestion, which is a multi-agent collaborative planning and decision support algorithm. So one of the caveats with this domain is that this is a shared goal, but the teams have different heterogeneous capabilities. For a team to succeed here, they require an effective live communication between the teams for collaboration and to establish shared situational awareness. So this is where visual information is better than the verbal information, and the environment where we need to communicate a complex, evolving, and data is re-reference. That is, we want to reference the data again and again by pointing it out or showing some sort of update. Visual communication has been like communicating data visually leads to better comprehension compared to the verbal communication. Additionally, the previous research has shown that visual communication has been employed in various search and rescue domains for data fusion and communicating intent. Specifically, we leverage the new hardware in the form of augmented reality headsets to show this visualization directly in environmental context without incurring the cost of frequent context switching to a separate device or to receive or pass information. Unfortunately, we did not think IRB would approve us for a live rescue operation in the Colorado mountain. So we abstracted the avalanche rescue into 3D Minesweeper games. So the goal of the game is to locate all 4 mines hidden throughout the grid within these boxes. A virtual drone can explore the grid using its noisy sensor to attempt to determine whether a box contains a hidden mine. Only human has, however, the capability of opening the boxes and defuse each mine. So the game was turn-based with human and drones alternating the action, and humans can move north, south, east, west, and open a box in attempt to defuse the mine, progressing towards the victory if there is a mine, or else wasting the time. So to give an overview of some of the characterization which we use, so MAS uses what we call shared dynamically updating probability mass function to characterize the uncertainty in the environment. So which can be used as a joint reward function to solve a parallel Markov decision processes for both human and robot. So in the general formulation of this class of problem, we target human and autonomous agents to have a different goals and capabilities, similar to avalanche rescue, where human must dig out the people and the drone is tasked with reducing the uncertainty and finding the survivors. So these roles were encoded in separate human and robot MDPs. To quickly walk over how this algorithm works, so let's assume an search and rescue example with a human and a drone teammate within this 6x5 grid. Onto the grid is a projected heat map, which indicates a shared PMF with the color range from dark purple, indicating the low likelihood of finding the target, to bright yellow, indicating the high probability of finding a target. So the first step is we initialize the PMF and we solve a robot MDP to obtain optimal policy. We use this policy to obtain optimal actions for each robot and command them to take those actions. Agent or agents takes these actions. In its new state, drone takes an observation, which is used to update the PMF. Here we see a drone's current grid square turning bright yellow, indicating that the observation revealed a high target probability. This updated PMF is used to solve the human MDP. The action recommendation along with the updated PMF is sent to human to be visualized via augmented reality headset. One thing which I want to emphasize here is we are suggesting humans to take action, but whether they take the advice or not is up to them. And human then uses the guidance to take their next action, which is recorded along with the local reward the human recovers from the action. And we repeat this loop till all objectives are achieved. So in the user study, we varied the type of AR guidance we provided to the participants. So we had prescriptive guidance, which is shown here as an waypoint arrows and a flag at the end of it, which shows the diffuse action. For descriptive guidance, we had a probability mass function laid out on the ground, indicating the likelihood of finding mines, and we had combination of both. For measurement metric, we had validated trust scales, interpretability scales, and mental load scale. We also had objective metrics in the form of performance, which is total moves, total time, and time per move. And we also had this objective metrics about how independent people are, which was measured through compliance rate. That is how much percentage of time did people comply with the recommendations provided by the agent. To summarize the results, people found the combined guidance to be more trustworthy and helpful for decision making. Interestingly, people found the prescriptive guidance to be more taxing, which was contrary to our hypothesis. Our initial intuition was that in prescriptive guidance, people would default to system one automatic thinking because they just have to follow the suggestion and it would be less taxing. Instead, we noticed that when drones would find a new mine, it would change its plan abruptly, That is, previously, if it was suggesting you to go left, it would suddenly switch to the right, which was frustrating to the people and they didn't know why. So that became more taxing for them. For the objective metric, we found that people solved the task quicker in the combined guidance and the prescriptive guidance. One of the interesting finding was for our independence hypothesis. We showed that the participants deviated more from the path in the combined guidance that is shown on the right. But on the left graph, you can see that the participants who deviated from the prescribed path was correlated with degraded performance in the prescriptive guidance, but not in the combined guidance. What it indicates is that in the combined guidance, people can leverage contextual information to take their own independent action without taking any performance hit. To summarize this work, so providing visual insights into robust decision-making along with the suggestion improves trust, interpretability, and performance, and also allows human collaborators to act more independently, choosing for themselves when to follow or ignore the robot suggestion. The core takeaway is that we want to give control back to the people when it is most needed, and this is one way to do it. Some of the caveats with this work is that we always had a visual information on, which can be cognitive demanding, and we did not explore the semantic justification in this work. Due to shift in distribution, guidance switched abruptly that led to drop in trust and compliance. As I mentioned earlier, if a drone found a new mine in the opposite side, it suddenly provided a switchback. That is, at one moment, agent is telling you to go straight, and suddenly it tells you to go back. People were frustrated when it happened, and they wanted to know why an agent was doing this. We also know justification can preemptively repair trust or reinforce the trust. So this is where we, in our recent work, we looked into how to time the explanation and what should go within those explanations such that it has an intended effect. So this is a work we recently presented at RSS, which I did with Matthew Lubers, Kyler Rubin, and my advisor. So there have been plenty of work in explainability to show its benefit. Like explainability has been shown that it improves human-robot teaming by improving situational awareness and improving collaboration. It has been leveraged to generate explicable plans to improve human trust. It has been used for explaining failures, debugging the controllers, and repairing and calibrating the human trust. So one of the things which is underexplored within this sphere of thing is when are such explanations useful? If you provide too many or too frequent explanation, people will be habituated to them and explanation will lose their purpose. If we don't provide them sufficiently and robot behaves unexpectedly than we expect, then people will lose trust in the system. So in this work, we basically explored when those explanations are useful and what should go in those explanations. So for that purpose, we explicitly defined justification as explanations timed at a mismatch expectations between agents with an intent of either convincing or influencing the human agent. Going back to this Morse loop of multi-agent RL, we added this justification framework that decides when to justify and what to be included in that. So for justification timing, we decided a novel mathematical framework based on the value of information theory that decides when an agent should provide justification. Value of information theory looks into the amount a decision maker is willing to pay for the information. So in this case, an agent would consider the added benefit of providing justification to the user and also consider the costs such as added stress, workload, and decide whether this is a good time to intervene and provide the justification or wait for it. So going into a little bit of detail, so we looked into the expected mismatch in the reward. So here we have robots expected mismatch, that is RH. Robot is constantly receiving new information, updating its reward function, whereas human is still operating with the old reward function RH had, as the robot has yet not communicated this information to the human. Similarly, we have expected mismatch in trajectories. So here, humans' expected path is without the new advice, and robots' recommended path is the presumed agent model that incorporates the new advice or the information. So we use a piecewise linear filter to capture the aspect of these each metrics and reduce them to a scalar component and compare it with the cost of providing a new information. So we justify only if the expected benefit to the user is higher than the cost of the justification. And we ran a user study to investigate the utility of our value of information framework. And in the user study, participants were asked to watch the videos of human agents task with justification presented using varying timing strategies. So we provided justification every time step, justifying on fixed time interval, and also with our value of information based approach. And we found that our VOI based approach was rated significantly higher than the other timing approach. Moving towards the content of the justification. So we looked into 4 different types of counterfactual justifications. These justifications are drawn from the previous work in explainable AI and are grounded in reinforcement learning literature. On the first axis, we had justification basis, that is environment-based justification and policy-based justification. And environment-based justification comes from the specific environment features that affected the policy of that agent. Whereas policy-based justification looks into an outcome of that policy. These can be related to actions or trajectories. I will provide an example just after this slide. So wait for it. The second axis is basically on the scope, that is local versus global. So local justifications are grounded in short horizon context and subgoals, whereas global justifications are grounded in long horizon task and reasoning. So here's an example of policy-based justification and environment-based justification implemented within our AR-based testbed, similar to Minesweeper domain. You can see in the left side, the policy-based justification, the system shows how many targets you will receive if you follow the new suggestion, which is shown in cyan, compared to the old suggestion shown in gray. Similarly, in the environment-based justification, the system shows the likelihood of finding the target in the new location compared to the old location in the gray. So this is shown in the right side. We investigated the utility of different types of justification using a user study involving a partially observable treasure hunting domain. Here, the goal of the task is to find as many treasures as possible in a limited number of time steps. Drones with noisy sensor searched the maze and provided recommendations similar to the Mars framework. Drones would justify recommendations via VOI using one of the 4 following justifications plus control where there was no justification. So going into the justifications which we use, so we had policy-based justification. So if you look into the top left, policy local justification is shown, which provided how many average moves it takes to reach treasure compared to the old recommendation. Within the policy global, which is shown on the top right, an average, it shows like how many average total treasures human will be able to find compared to the old path. Going into the environment-based justification, we had environment local justification that provides the likelihood of finding the next treasure compared to the old one. Whereas environment global justification provides a full reward function as a heat map. So within environment-based justifications, these are animated and cycled between old and new recommendation and percentages as we are comparing the two reward function. So we ran a human subject study using Amazon Mechanical Turk with 5 conditions as mentioned earlier. We had similar subjective and objective measures as in Mars, like number of targets found, compliance rate, etc. So what we found was, people subjectively preferred environment-based guidance, and they rated it in a higher perception of interpretability, intelligence, and trustworthiness. Whereas policy-based justification led to higher compliance and faster decision-making. So this is an interesting finding. Like, people subjectively preferred environment-based justification, but were more compliant on policy-based justification. Another interesting take here is that policy-based justification led to higher performance in our experiment. This is because within our domain, agent recommendation had higher competence, and policy-based justification led to higher compliance. On the contrary, if the agent recommendations were bad, it would have led to a worse performance. It is an interesting dichotomy of results. So we use this differential applicability of environment-based justification and policy-based justification to come up with this matrix of finding. I would encourage you guys to consult the paper to find a specific guidance and when to use them for your use case. But to provide a high-level overview, the core insight is to use a policy-based justification when a robot has higher competence than the human in that environment, as it is easy to understand and promotes higher compliance. We recommend using environment-based justification when human has higher competence compared to the robot, as it is more informative and promotes active thinking pattern. And with this, I would like to conclude. And here is the summary of the 4 work I just mentioned. And I would like to thank Talking Robotics for hosting me. I'd like to thank my advisor for his continuous support and guidance. And special thanks to all my collaborators. And finally, our research sponsors. Cool.
Thanks for your talk. Aaquib, it was great to hear about your research. If you now we have some time to take questions.
Could I ask real quick, which robots you had used for the first study that you had talked about?
We had a Sawyer, Rethink Sawyer, if you know. It's a
Yes.
Yeah.
I don't have a question, but I just wanted to say it was very interesting. I was already very curious to hear more about your work since we talked last time, and I now think I had a clear idea of your
It's
line
nice to
of
see you,
work.
Carolina.
Yeah,
It's been a
very
while.
nice to see you. So yeah, it was a great talk. It's very nice to see all this type of studies. It's also very in line with what I do, and I think it's really interesting to, yeah, all this hypothesis you have on how people will behave, and then they just do something else, and you have to try to understand why that happens. Something
Yeah,
I'm very familiar with as well.
This is one thing which I'm very excited about. Like, within the AI community, the one thing which I've seen is, like, they don't consider people into picture when they are designing the system. So that's,
Exactly.
I feel like our work is kind of very important when it comes to that.
Yeah, exactly. I try to do the same, but it yeah, can be very frustrating sometimes, as you know, for sure, but can be highly rewarding as well.
Yeah.
Very nice work.
I have another quick question. So I know you had mentioned working with Sawyer and I think drones and some of the other projects, but have you like worked with humanoid robots, such as like now, and if you've employed those types of robots in your study?
No, I haven't looked into a humanoid robot. So we try to anthropomorphize it by, like, priming people, but we haven't. So especially with the Sawyer robot, I usually try to do is like put a image on the monitor
Right.
just so that people think it is like, oh yeah, it has an embodiment, and that's where it comes to it. But it's an interesting question, like how the things change with the anthropomorphism.
Right. Cool. Thank you again for your talk. It was super interesting.
Thank you.
Yeah, I have maybe a question if I can ask. It's just it's a bit more something I also come across frequently. So you mentioned this type of collaboration in a way of helping the human to achieve their goals. And I wonder if you know if people see the this collaboration as teamwork in a way, if they do recognize the AI as a teammate or team member, or it's not like it's super relevant, it's just something that comes across. It came up in one of my studies that I asked something about their teammates, and they were just like, who was my teammate? So this is just something I'm just curious to see what's your perspective on that.
I think it depends. I feel like sometimes we just get we anthropomorphize many things. And we have one of the study which is happening in our lab as well, where we are trying to see like, oh, different types of AI assistants with the personalities, how do people relate with them? And I feel like depending upon the task, I think you can nudge them to consider them as a teammate or not. That's my initial intuition towards it. But it's an interesting study. Like, yeah, like sometimes when I use ChatGPT, sometimes I can say, yeah, I'm collaborating with ChatGPT, but sometimes I'm like, oh no, I'm using it as a tool.
Yeah, as a tool. Yeah, exactly. There's always that discussion on what makes it a teammate or not. It's a bit more philosophical question, and I think for us most of the times doesn't really matter at the end of the day what term people prefer to use. But since you are using also an explanations, I was also wondering if you found that.
I think
Yeah.
so the language here is a very important thing. So the I'm assuming you're familiar with some of the work from Tom Williams' lab.
Yeah.
So he is very much big on this idea that, okay, how different characteristics comes into the picture when you enable robots with language and they start enabling like moral agencies and all those teammate agencies and everything. So I think it kind of relates back to that, like, okay, we have a team person who is speaking back with us, then yes, definitely there might be some angle there.
Yeah. And maybe one more question. I don't want to dominate this conversation, so like my last question before I shut up for now. And because we also see many times in this type of studies that, for example, because you also measured trust and other things, many times I feel like people are so focused into just finishing the task. For example, finding the target, and of course they will read these things, but they are not like consciously noticing that there's like an AI helping them, or do you understand what I mean?
Yeah, totally. So they default into something of their like little bit on the primalistic behavior. So this happened within our first study. So with the Sawyer. So we told them, oh yeah, you're collaborating. The robot is helping them. And when they went into the core of it, they just started ignoring the robot's advice because, okay, I thought, and when we later asked them, they said, oh no, actually, I thought it was a competitive game. And I thought I have to perform better than the robot.
Yeah, this is super interesting because if it's, so for example, I think in your case, because you also create different types of interdependence and they really need the advice sometimes to not survive, but to make it, they are kind of forced to pay attention to that. But also in some of our studies, I feel like sometimes there is a chat with things that the AI is saying, but if it's not like crucial for what they are doing, many participants don't even take a look. They are just so focused in finishing the task that they just ignore completely the surroundings of it. And it's sometimes hard to compare conditions if the nuances are not really in the task itself, because people just completely forget even the scenario. They just care about what really affects their performance in the task, which is yeah, very annoying sometimes.
Yep.
I have a quick question. Thank you for your awesome presentation. I feel more interested in the later part of your research. So when you apply, like when you talked about justification scope, there were two kinds, local and global. And you described short horizon context as a local one and long horizon context as a global one. Could you explain more about them?
Yeah, sure. So the idea behind that is more like you can think our initial motivation was marshmallow test. So basically like, oh, can we influence people's behavior by saying like, okay, you're gonna get something in a short time versus, oh, if you wait a little longer in a longer horizon, you will have a better reward. So we wanted to scope it out saying like, okay, people will be very much influenced with the shorter or longer horizon. But the core intuition is that like we want to employ this depending upon the context. Like in some scenarios, it's better to have like a short horizon, like you cannot plan for a long term. And it might be better to show people just a short-term horizon benefit, which would help them. But if you can have some idea about a long-term horizon, you can use those as metrics to show them, okay, this is the reason why I'm telling you to do this. You may not see it now, but over the long period of time, this is the better choice for you, if that makes sense.
In terms of getting more rewards?
Yes, more reward or more like, how do you, it's more like a framing strategy, like saying like, I will give you one marshmallow now versus I will give you 2 marshmallow later on if you do this kind of thing.
Okay, so because the algorithm can predict, it could,
Yes.
you can kind of, differentiate the, horizontal lengths, I guess.
And
The other go ahead, please.
no, I was just gonna mention that like it would depend upon your scenario. So that's the reason we came up with this matrix, which I was showing you that like when and each explanation would be helpful. Like for local explanation is good when you're trying to come up with like low thinking time and you just want to motivate them to take quick actions, something like that, if that makes sense.
Oh, I see. Okay.
Yeah.
And I had another question regarding timing justification. So on the slide, expected mismatch in rewards and the one in trajectory, like how did you distinguish humans expected path and plan versus robots recommended path? And how did you come up with a value of mental workload?
So workload for now, we did not specifically use, like we basically use the idea of our like, so coming back to the first question. So differentiating between the current human path versus the new path, it is the idea that we are operating with the faulty reward function. So they have a current path which they are following. And now the robot receives the new information. So it has a better path. So for example, if it receives something new, which leads to a divergence of the path, so it needs to communicate that back to justify that path divergence. So to give an example, like you're driving back to home and you're very much familiar with the road, but suddenly the GPS says to go the long way around. This is where there is a mismatch in expectation, and you need to explain this to the human saying that, okay, there is an accident on the way to your home. That's why I'm taking you a longer way around, if that makes sense.
Yes. Okay.
And for the cognitive load question, so the idea is like we ad hoc it based on how much busy the people were. But our future work currently looks into a little bit on like using some sort of physio signals. So we are exploring a bit of like eye gaze tracking and some sort of like physiometrics to see how busy the people are, how stressed they are. Based on that, deciding when would be a good time to provide this information. Like if they are already stressed or they're about to do something, it may not be a good time to intervene.
Right. All right. Thank you. It's a very inspiring work of mine
Thank
because I'm
you.
trying to find out if there are any aspects that I can adapt to my automated driving environment in terms of like making interventions in the conversation, or like recommending something to the human driver from the intelligent agent in automated driving context.
Yeah, automated driving is a very difficult. I've explored a little bit on this, and I know like it is a time critical. So you need to be very quick with anything which you do in that domain.
Right. Yeah.
I know the challenges of that.
Thank you, Aaquib.
Thank you. Feel free to reach out to me if you have more questions.
Sure, I'll definitely find you in LinkedIn. All right, thanks.
Hey, thanks, Aaquib. That was a wonderful session, and I'm pretty sure
Thank you so much for inviting me. This was really fun.
discussions were
So, yeah.
crazy helpful, insightful as well.